Mankind's insatiable curiosity for its surrounding environments eventually led to inquiries of those beyond our planet. In order to explore the dangerous and unforgiving frontier of space, the first barrier to overcome is the engineering of a craft that can propel itself beyond Earth's gravitational pull and maneuver its trajectory through the vacuum of the cosmos. The fundamental ideology behind this technology to explore the stars originated from observing the Earth. From the simple phenomena of an apple falling from a tree, Isaac Newton pondered and developed ideas about gravitational attraction and forces. Among the pool of scientific concepts he gave to the world lies Newton's third law. For every action, there is an equal and opposite reaction.
3, 2, 1.
Houston is controlling. 16 seconds, Metropole program started, 14 maneuvering, flight course.
The initial momentum of the system is equal to mass m of the rocket times its velocity v. As time passes, the rocket loses mass but gains velocity. The ejected fuel has the same amount of mass the rocket has lost and is moving at velocity u relative to the ground. The final momentum of the system is equal to the momentum of the ejected fuel added to the momentum of the rocket. This equation can be simplified by using the velocity of the fuel relative to the rocket. A substitution into the equation and a couple lines of algebra reveal the following equation, mathematically proving the equivalence to Newton's second law. In order to propel a rocket to escape velocity, one must design a mighty internal combustion engine with the proper materials and a physique powerful enough to combat and escape the tenacious clutch of Earth's gravitational pull. A rocket engine consists of two main parts, the chamber and the nozzle. The chamber hosts the interaction of the high pressure and temperature propellants and is of sufficient length to ensure their complete combustion before the gases enter the nozzle. The nozzle converts high pressure, low velocity gases in the chamber into low pressure, high velocity gases at the nozzle exit. The nozzle itself is divided into a convergent and divergent section. The maximum cross-sectional area is at the nozzle exit, and the minimum cross-sectional area is at the nozzle throat, the key to producing high-velocity gas. A desirable engine design calls for both a high contraction ratio and a large expansion ratio. This way, speeds of both subsonic gas flow above the throat of the nozzle, which accelerate when compressed, and supersonic gas flow below, which accelerate when expanded, can be maximized. From submarine ventures into the deep oceans to the soaring aircraft that join birds in the sky, humanity has always held a relentless itch to explore forbidden frontiers. As is the nature of mankind, innovation hasn't ceased at internal combustion. Ion thrusters, common tools of propulsion among satellites, utilize the science of electrostatics to propel spacecraft already gracing the vacuum of space. Both hold great potential, but still have yet to come to fruition in accomplishing the goal of bringing our species closer to establishing a multi-planetary presence. Carl Sagan spoke of such dreams. He said, "But those are the worlds promising untold opportunities beckon. Silently, they orbit the sun, waiting."